Hello, grade 8. This is your first lesson. This one is on work, which is what you all should be doing. But before we even get started, I need you to do this warm-up. So pause the video. You're pausing right at the very beginning. And you are going to complete warm-up, M1a, and then get back to me. Okay, so these are the answers for the 5 points of the particle model. Everything is made from particles in a pure substance. They're all the same particles. Particles have space between them. They always have motion and they attract. A car is not considered alive if it responds and adapts to environment because it does not grow and it does not reproduce. And fluorescent light is that UV light being absorbed by particles to let visible light be released. Okay, so let's get started on the first little section here. Now, I am assuming that you have watched these two videos. The two videos that are shown here, they were set for you to watch them before you watch this video. So if you've not watched them, please go back and watch those sections. So, what is a lever? A lever is a simple machine that changes the amount of force needed to move an object. So a lever could wind up actually increasing the amount of force that you use or decreasing the amount of force you use. And we can use them either way. Okay, so a lever consists about a bar that's going around a fixed point, and that is called the fulcrum, which supports the lever and is the point of rotation. The force that you put into the lever is known as the effort force. That is the force that you are putting in on this. The load is simply the mass that is being lifted on the other part of the lever. So the distance between the fulcrum and the effort force is called the effort arm. And the distance between the fulcrum and the load is called the load arm. Now, taking a look at figure 4.2, right, you can copy this straight from your textbook. You've got what we call the fulcrum. You've got the load. And you've got the effort force. And so in this scenario, this distance is called the load arm. This section is called the load arm. And this section is called the effort arm. Now, in this case here, yes, you could actually, this is where we're actually putting the effort in, right? And this is load being lifted up. But with this fulcrum, we very easily could make this the effort side and the other side the load side. We can sort levers into 3 different categories. Okay, so those 3 different categories can essentially be determined by what is in the middle. In each case, it's always look to what's in the middle. So if we were to take a look at this first one, we've got the fulcrum, the load, and the effort. The fulcrum is in the middle. That is the key thing within a class 1 lever. Fulcrum in the middle. Your load and effort are going to be on either side. With a class 2 lever, we've got the fulcrum over here, the load in the middle, and the effort happening at the end. And so within a class 2 lever, the load is in the middle. And so you can probably guess already, class 3 levers will have the fulcrum on the one side, the effort in the middle, and the load happening at the end. And so we've got the effort in the middle with a class 3 lever. So taking a look at each one of these devices, This point here is your fulcrum because that is the point of rotation. On the tweezers here, you're going to use this as a load because that's what you're picking up, and you hold them right here. So this actually helps you with your effort, and so it is a Class 3 lever. Class 3 levers are usually good for gaining lots of precision. Here, we've got, with the set of pliers, we've got the fulcrum in the middle, your effort on this side, your load on this side, and because your fulcrum is in the middle, this is a Class 1 lever. And lastly, with the nutcracker, you probably already guessed here, fulcrum's here, the effort's here, because this is where our hands will be, is trying to crack the nut in the middle, and so the load is in the middle, so this one is the Class 2 lever. So through much of this, your bones actually act as levers, or arms of a lever, and your joints actually act as the fulcrums within your body. And so when a muscle contracts, it exerts an effort force on the bone, and this, the load is something that you're lifting or pulling with your own body. So, what is work? This whole lesson is entitled Work, so knowing what work is important. In work, science has a very specific definition of work. It is when you exert a force on an object and move that object some distance. Now, it is important to note that this must be within the direction of the force. I'm not doing any work if I push something north and it moves west. This formula here can be found on your formula sheet, and it's just force times distance. This is the amount of work that is being done. It's really just energy in action. Energy, as you may recall, is the ability to cause a change. Work is the change that is being done. And so it has the same units as energy, which we use the standard unit of joules. So let's take a look at a few examples. So the first one here. Vivian and Christy are having a tug of war with their gym teacher. The distance to pull was 3 meters. They pulled as hard as they could, but they could not move him. Assuming the teacher's mass is 90 kilograms and Vivian and Christy pulled with a force of 800 newtons, how much work did they do? Well, in this case here, work is equal to the force times the distance. Now, they applied 800 newtons of force, but the distance that they moved him was 0. Therefore, 0 joules of work have happened. In Smiley Joe's garage, customer has an engine of 221 kilograms and has to lift it out entirely a distance of this. Now, you're given this hint here. To convert kilograms into newtons, you got to multiply by 10. So the hint is there. Let's use that. The amount of force is just going to be 221 times 10, or 2,210 newtons of force. Now, this is assuming that we're on Earth. Now we can actually do our calculation. Work is force times distance. That force being 2,210 newtons multiplied by a distance of 1.5 means that the amount of work done is 3,350 joules of work. Next question. To assist in a demonstration, student has 60 kilograms, fills a water balloon with 2 kilograms of water, then climbed to the second floor, which is 10 meters above the ground, and held the balloon out the window. How much work did they do to the balloon? Well, if you think about it, this student is going up 10 meters with a 2 kilogram balloon. Right? That's my balloon there. Now, the fact that he's 60 kilograms doesn't have any bearing on this question at all. It's the 2 kilograms being lifted up 10 meters. Again, we're going to need to turn that into newtons, which would be 20 newtons. We don't worry about the 60 because we're not worried about the work done to the student. We're done to the work done to the balloon. 20 newtons of force is required for that. Force times distance. So the amount of work, 20 newtons times 10 meters, that gets you 200 joules of work being done. Now, with some glee, the class watching from a safe and dry distance below, that student drops the balloon and hits the sidewalk. The balloon hits the sidewalk with a force of 20 newtons. How much work is done on the sidewalk by the balloon? Right? We want to know the work done on the sidewalk. Right? Now, in this case, force times distance, 20 newtons of force, we're going to multiply that by 0. The sidewalk does not move, which means the total amount of work done is 0. Now, I know the balloon fell 10 meters. That is not the point. Now, if we take a look at the inclined plane, the inclined plane is designed for us to reduce the amount of force needed to lift things. It's going to reduce the amount of force. So if we take a look, that's going to be 100 newtons multiplied by 1 meter will get us 100 joules of work. Or 50 newtons if we go 2 meters. Again, the same amount of work is being done. It's just taking a little bit longer, but half the amount of effort required. 20 newtons times 5 would also equal 100, or 10 times 10, or 2 times 5, or 1 newton times 100 meters. Again, same amount of work, but 1 newton is a lot easier than 100 newtons, but it takes a whole lot longer. So if we were to take a look at these scenarios, the easiest way of doing this is going to be done within example F. Why? Because it's the least force, right? But most distance. The fastest way would be within example A because it had the least distance. Right? But took the most effort, but most force. So when we take a look at these two ramps, both going to a height of 2 meters, student decides to use ramp B to move cases into the school. Why did you choose that choice? Well, the distance that they're doing is a lot longer. The height is the same, but going through a greater amount of distance, same amount of work being done to lift the juices up, but doing this over more distance, right? More distance means less force. So probably did this because it is the easiest way to do it. It's because it is easy. Okay, hope that helps. Thanks for watching.